Okay, here we are for take two. Sorry about that. I got a super important meeting. I say sorry about that as if someone was watching this, but I got a super important call and I had to take it. Audio is working and stream is working, and so I'll get right back into it. Good afternoon, everyone, and welcome to Tea with Chloe in the afternoon. Got some honey lemon tea here. And yeah, it's been an interesting week, but we're back on track. I think I already read through the chapter on Intro to Mathematical Cryptography, and yes, I'll make sure to do my intro as well. I'm Chloe Lewis, co-founder of the Marma J Foundation, lead of Marma J Labs, and just kind of working to support education, cryptography education specifically at the moment. And so to do that, I am engaging in the Uncloak Cryptography Engineering Study Group. That's what I have over here on the right-hand side of my screen. We're at session 10, week 10. Well, we didn't really do it week by week, so session 10 of the course. And we're kind of getting into the math behind cryptography now. We did a lot of theory and get kind of a lot of like how pieces fit together over the past kind of 8-9 weeks. Week 9 kind of started getting into the math side of things from a high level, and now we're kind of digging a lot deeper, I would say, actually. And so there's a few exercises at the end, and I'll kind of go through those first to kind of shape the context of what we're doing and why we're doing it, potentially. If anyone does happen along this video and you're like, what the heck's going on, you can just go to the link in the description and just go to the exercises. And maybe you're better at math than me and you can just go straight to it. Please don't sit here and watch my stream. Just go straight to the link. Also, Thor does stream this content on the Uncloak YouTube channel, so please just go through the channel, watch or listen to that stream, and kind of you can go through the content yourself. This is just me going through it, so I can take some notes on the left hand side here, and keep myself accountable to my educational journey, I guess, my research journey. Okay, so it was an optional exercise. So recalculate by EEA. I can't even see, this is my brain right now. I can't even remember extended Euclidean algorithm. Ha! There you go. Recalculate by the extended Euclidean algorithm the inverse of 397 in the group modulo 2,357 with the tabular method given on page 19. So we know already we're going to look for something on page 19. So this is kind of, again, what the notes are for me. I'm kind of switching up my note-taking a lot. That'll probably be very evident as I go through this. I used to do a lot of copying and pasting and a lot of kind of just rewording things to go back through it later more efficiently. And now I realize I don't have time to go back through anything, and so I just kind of need notes to just help me kind of answer a question or solve a problem or be able to kind of go back through like a month later and still know what's going on. So anyways, for now, page 19. Implement the modular fast powering algorithm for big ints. So looks like I'm going to have to worry about the modular fast powering algorithm. Let's just put it up there. Why not? It's not that many things. For a positive a and b, which are real numbers, suppose that there exists a u and a b that satisfies AU plus BV equals 1. And this always, I read it, I understand it, but honestly I'm just going to put this here. Because I get what it's talking about already. Doing some proving the GCD is actually 1. There's some algorithm you can actually use, and so obviously it's saying, hey, implement this algorithm. You can go to the solutions and see how it's done as well. Next question, suppose that G to the A is congruent to 1 mod M, and G to the B is congruent to 1 mod M. Prove. Ooh, this is a good one. Proofs are hard for me, like very, 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 very non-intuitive for me, like just absolutely complete, like just, yeah, not intuitive for me. But I go through them like dozens of times, and I still barely get them. But I'm starting to somewhat get them, at least with cryptography, because I understand why they're useful. And that's kind of why I like the math side of things. So using a program, so this is actually the hardest part for me so far. A lot of modular arithmetic, particularly the intro parts of it, I'm starting to understand how it starts to fit together and what pieces are important. But the whole like something's a generative of a group if it goes through every number of a group without repeating. But obtaining a generator is like the hard part for me. Like, I get what a generator is, but then actually figuring out how to use it or how to find it is tough. Both values are prime. So it's saying, like, I guess this value is prime and this value is prime, and you're trying to find a generator that can generate over both of these. So how did you do it? And there's obviously a program for finding generators, or like taking two values and finding their GCD, and then maybe that would be the way to do it, right? Take two primes and then find the GCD, and maybe that would give you the generator. I did have some code from last week that I might just try and run, and maybe it'll help. I don't know. Code dot. Oh no. CD. What do I have here? Sorry, I'm trying to. What did I just do? Oops. Okay. Cargo build. Cargo run. Okay. So this is a small little thing I kind of wrote, but 1009, value of B, 2, 3, 5, 7, and then it's saying, so now, that's not helpful. So this is just the first part. This is like the extended utility algorithm or whatever, from like week 8. And this is why it's from week 8. So now I need to find what the generator is, and that's what I cannot remember for the life of me how it's done. So I'm excited to kind of dig into that more. But anyways, we're going to go through the actual course material now. Actually, I should say after GCD equals 1 is known, find G. So those are like my things that I'm like, okay, I need to figure these things out because I'm struggling. Okay, so this week we'll be shifting to a more mathematical coverage of cryptography. For the next 4 weeks, we'll be covering from sections from Introduction to Mathematical Cryptography. So, if you don't know where to find this textbook, you can just click Session 9 notes up here. It'll put you back a session. There's a little link right here in Introduction to Mathematical. I'm actually going to... Okay, give me a second. I'm going to copy this link. I am going to go to, I mean, you can just click it, you can open it up, you can download the textbook, and you'll get it right here. But what I'm going to do is go to GitHub. Maybe I'll do this properly. Just because it's so much easier when the link's just right there. And I know it's so easy to find, but why am I saying, like, I keep going, oh, I'll fix it later, or I'll do this, but, like, sometimes, wait, session 10, come on, session 10, notes, okay, and let's just do a simple one, okay. screen is just really small. Sorry. From do I have to put think I have to put this in square brackets? I think. Preview. Yeah, there you go. And if this is literally all I can do to help, there you go. So this is just literally all I do. I kind of just go stream. I didn't change anything here. There you go. Nothing changed. I don't know why it's saying so much has changed. Maybe because it got pushed down by one? Yeah, it got pushed down by a line. Okay, so I'll keep that open just in case I see anything else that I want to change as I'm going through it. But this is pretty much, sorry about that, what I'll be doing for the next little while. I will put that back over here. And I will go back to session 10. Okay, this week's coverage is a partial review of chapters 12 and 13 of Cryptography Engineering with a closer eye to detail. So, from the Cryptography Engineering textbook, I did stream a lot of that, like up to chapter like 6, 7, quite extensively. Then I kind of got busy with Marma JCon and Christmas and a bunch of other things. So I have not gone through as much of chapter 12 and 13, in detail studying it. And that's definitely to my detriment. But I'll definitely try and go back to those chapters when I have some free time. If you are inexperienced at reading mathematical text, some advice. Of greatest importance are definitions, and this is kind of what I need to work on, is just getting the definitions for everything so I can use little search bar in here later and find them. A thorough student will copy each definition to the notes. All the theorems and results follow directly from the definitions. Much of the difficulty, mathematical definitions, much of the difficulty in mathematical development. Oh, I didn't even create the pull request yet. My bad. Why so many clicks? Okay. Sorry. I already read this and it kind of, whoops, wrong one. I already read this and it kind of confused me a bit. And now I'm reading it again and I'm like, okay, maybe I should just, maybe it's not supposed to be there. So sorry, I'm going to do this one as well. Much of the difficulty, I'll just put with maybe. Much of the difficulty with mathematical development, in mathematical development, I kind of wanted to say much of the difficult mathematical development is simply obtaining the correct definitions. I might just do that. Much of the difficult mathematical... Okay, this whole sentence is stressing me out. I'm sorry. Much of the difficulty with mathematical development. Much of the difficult stresses me out. Much of the difficulty sounds better. Much of the difficulty with... That's not how you spell with. Much of the difficulty with mathematical development is simply obtaining the correct definitions. Okay, I'm just going to keep this open for now because I might have more edits and I don't want to keep doing PRs for that. it was silly through the first one, but I just wanted to get it in. Okay. Second, try to understand the crux of each algorithm, theorem, lemma, and proposition, and summarizing in a sentence for your reference. For instance, the fundamental theorem of arithmetic, yeah, it says arithmetic. I just can't read today. States that if, and I can't really copy and paste here, so I'll get it myself later. States that if n is greater than 1 and is a real number, then n may be factored into the product of primes. That is, for all n greater than 1 a real number, there's just a unique factorization p of I and e of I such that n is, for the product of all I, pi, that's one of a, ei, the greatest common denominator. And this is where I'm gonna have problems. Sometimes reading these out, like I have to sit there for a second and like be like, what are you trying to say again? The greatest common denominator of A and B minus the set of 0, maybe that's restated. GCD of A and B equals the product of I for P min. Okay, that I don't know what min is there for. EI B. Where is A and B coming from? Oh, here. Sorry, the greater than AB. Maybe that's restated. Oh, minimum, because you just want the smallest one. There you go. I was like, what's happening? Smallest factors of A and B. Okay, but an easy to remember one sentence summary should help recall the theorem. For instance, okay, see, this is not that helpful for me, but every positive integer has a unique prime factorization is much easier to remember. I'm sorry, but this does not help me uniquely recall this. But to find the GCD for A and B for all the I, each product of I, you have one of the primes, I guess maybe the bigger prime or the smaller prime, maybe it doesn't matter. You take the minimum of the exponent. That seems complicated either way. I'm not good with proofs though. So try to understand the proofs, but don't fret if they don't come naturally to you. Proofs often reveal not only the reasoning behind the theorem, but even motivation to further theorems and corollaries. My gosh. However, proofs are often the hardest part of reading mathematical text. I will attest to that. Only spend as much time as necessary learning proofs. You decide what necessary means. Okay, so I'm going to spend maybe 2 to 5 minutes on each proof. Longer than that on my own, but not on the stream. The goal of this week is to give more complete introduction to mathematical tools using public key cryptography. Pay most attention to sections 1.2 to 1.5. I kind of just like that in general, just to keep an eye on. We start in section 1.2 on divisibility, which should remind the reader about basic facts on divisibility, GCD, the division algorithm, Euclidean algorithm, covered in crypto engineering chapter 10. Section 1.2 is an opportunity to review in detail coverage of the extended Euclidean algorithm, EEA, I guess, is what's being referred to many times, which guarantees that we can easily obtain modular inverses. So I was doing some like GCD algorithm, and then I guess maybe the modular inverse would help me find the generator, and maybe that's what I needed to do for this one here. Anyways, The EA is also is an incredibly useful algorithm. The tabular method given on page 19 may be of help in calculating it by hand. Which sounds cool. I'll probably try and do it once, literally with what it gave here. But wow, that sounds like a pain in my butt. It literally sounds like the one reason why I want to learn Rust is because or programming in general, is because I dislike like doing math. I love math theory, but actually doing math is very difficult for me. So calculator, computer makes it more efficient. Section 1.34 introduces some common notation in modular arithmetic, pays special attention to Euler's totient function and the fast powering algorithm. So Euler's totient function, I finally think I understand a little bit. I'm going to add that to the dictionary. But the fast powering algorithm, I feel like I just keep forgetting what is happening, and I need to just get a definition of it, like write it down and like have it here. So prime fields, which I actually feel like I finally understand a little bit now as well, are a central focus of 1.4. Makes you understand proposition 1.22. You may need to revisit the extended Euclidean argument is unclear. Okay. And this for me is just like a little one-pager cheat sheet as I go through the textbook again. Because I already went through the textbook in a general sense, but I definitely missed, some key things or something they take notes on or go over again. So, section 1.5 is the first non-review section. Take care to understand Fermat's little theorem and the primitive root theorem, which guarantees. Yes, this is the part that is why I lost this. This is what I lost. My brain did not pick this up. I was probably tired going through the first 4 sections. If you're familiar with Silo's first theorem, the primitive root theorem becomes trivial to prove. I don't know why that looked weird. 1.6 is optional. Historical notes. I found it pretty interesting, actually. I kind of liked 1.6. And 1.7 is optional, formalizing the mathematical notations of asymmetric and symmetric encryption and introducing the premise of binary encoding schemes. I also liked 1.7 quite a bit, actually. But apparently they're not as important for the actual, what's it called? For the course. So, now, 22-minute introduction to setting up week 10. And I'm going to try and start setting up the weeks on Mondays and use the weekends for reading the chapters on my own. So, we're getting there. But the traveling and the holidays don't make it easier. So a bunch of Brown professors, so thank you very much. And one from SFSU, so thanks to you as well for this wonderful textbook. It came out in 2008, from my understanding. Yeah, 2008. And I'm not going to go through all of the preface and everything like that, but I do think skimming it is pretty useful. I might zoom in a tiny bit, just because I think just for reading, it's nice to just. Let's see if this works. It does work. Awesome. So, let's get into it. The creation of public key cryptography by Diffie and Hellman in 1967. It's not even that long ago, maybe like 50 years ago now, going on 60 years. And the subsequent invention of RSA, public key crypto systems by RSA, Revest, Shamir, and Alderman, in 1978 are watershed events in the long history of secret communication. So that's kind of what we're talking about, secret communications. So whenever someone's like, "Oh, Chloe, what do you do?" And I'm like, "Well, I guess I'm kind of a cryptography researcher. Like I try and just dig into cryptography engineering." Like, what's that? It's just kind of secret communications. It's hard to overstate the importance of public key crypto systems and their associated digital signature schemes in the modern world of computers and the internet. Even more important now, since this book was written in 2008, I mean, we all know how much we're drawn to our phones and everything like that. And our phones use cryptography constantly, whether it's your fingerprint to log in or it's your login with Google, the button that you click to log into everything now. But this book provides an introduction to the theory of public key cryptography and to the mathematical ideas underlying that theory. And so I think this to me is kind of the key point. And maybe just because I'm not going to take a note of that, because normally I would, because I found it interesting, but I'm going to stop. This is where I'd want to highlight, actually. Color, purple, opacity, select. So maybe this will work. Okay, opacity. This isn't really what I want. Oh my gosh, this is so not what I want. But, it kind of worked. Public key cryptography draws on many areas of mathematics, including number theory, abstract algebra, probability, and information theory. Each of these topics introduced and developed in sufficient detail so that this book provides a self-contained course for the beginning student. So to me, that's kind of the important part there, is that you can kind of come into this book, be a beginner, and kind of get through it. So I'm going to kind of skip ahead. That's kind of the most important part. It's going through the math, and if you want to know the math behind crypto, this book might be right for you. It's going to go through an introduction to cryptography in chapter 1. That's what we're doing now. And then after that, we're going to go into, I'm going in order, and I'm going through probably the entire book. Hopefully, I keep saying that and then not doing it, but this time actually seems relatively reasonable. Discrete logs and Diffie-Hellman, integer factorization and RSA. I need help with this one for sure. Combinatorics, probability, and information theory. I'm also not the best with this. I just haven't really gone through it before, so I think it's important for me to get a background. Elliptic curve stuff, important in my opinion, because it's used a lot in blockchain cryptography. Lattices, there are a couple blockchains that use lattices. I don't know much about lattices at all, but it seems like a few blockchains or crypto ecosystems, whatever, are starting to use lattice cryptography instead of like typical blockchain cryptography, so that's interesting. And then digital signatures, which seems relatively straightforward, and then additional topics like zero knowledge and stuff like that, quantum computing and all that kind of craziness. But starting off very simply with an introduction, we are going to try and actually, get into things. So introduction. Actually, I should do this, and then I should do this, and then I should do this, right? Maybe? No. Nope. I should do this, and then I should do, what's it called again? I should actually label it, and then I can do that. There we go. It's good enough. Let's take that down. A principal goal of public key cryptography is to allow two people to exchange confidential information even if they had never met and can communicate only via a channel that is being monitored by an adversary. So this to me, okay, why are you not allowing me to just copy and paste this very easily? Even though I said I wasn't going to copy and paste that much, I will still be doing the first copy paste, and I don't know why this is formatted so weird. I actually don't know how to remove all formatting. Oh. Cut. And then paste as plain text. That is a positive. That's better. And so now I'm going to try my best to mainly just take down definitions, and yeah, it's hopefully honesty about it, and then maybe some of my own words about the definitions. So the security of communications and commerce in a digital age relies on the modern incarnation of the ancient art of codes and ciphers. Underlying the birth of modern cryptography is a great deal of fascinating mathematics, some of which has been developed for cryptographic applications, but much of which is taken from the classical mathematical canon. The principal goal of this book is to introduce the reader to a variety of mathematical topics while simultaneously integrating the mathematics into a description of modern public key cryptography. For thousands of years, all codes and ciphers relied on the assumption that the people attempting to communicate, call them Bob and Alice, shared a secret key that their adversary, call her Eve, did not possess. Bob would use the secret key to encrypt his message, Alice would use the same secret key to decrypt the message, and poor Eve, not knowing the secret key, would be unable to perform the decryption. And the disadvantages of these private key crypto systems were that, so again, we're talking about public key crypto systems now, and we're talking, this book is talking about public key crypto systems, and right now we're talking about the disadvantage of these old school private key crypto systems. Is that Bob and Alice need to exchange the secret key before they can get started. So Bob and Alice share some sort of secret, private secret key, and then the attacker, the adversary, Eve, who's trying to listen on the communication, is unable to do so because they don't have the secret password to access the information. During the 1970s, the astounding idea of public key cryptography burst into the scene. In a public key crypto system, Alice has two keys, a public encryption key, kpub, and a private secret decryption key, kpri. Alice publishes her public key, kpub, and then Adam and Bob and Carol and Carl and everyone else can use kpub to encrypt messages and send them to Alice. So you use your public key to encrypt the message, send it to Alice, and then Alice can... The idea underlying public key cryptography is that although everyone in the world knows kpub and can use it to encrypt message, only Alice can use the private key that she has to decrypt the message to Alice. So Alice cannot use her private key to decrypt a message to Carl, and Alice cannot use her private key to decrypt a message to Bob, but Adam, Bob, and Carl can all send messages using their own public keys to Alice, and Alice can decrypt them, because they make sure that only Alice can get them, using Alice's public key as well. The disadvantages of a public key crypto system are manifold. For example, Bob can send Alice an encrypted message even if they have never previously been in contact. But although public key cryptography is a fascinating theoretical concept, it is not at all clear how one might create a public key crypto system. Okay, well that's just incorrect, because since this textbook has been created, we definitely have many public key crypto systems, I'm pretty sure, but there you go. More precisely, one looks for a mathematical problem that is hard to solve a priori, but that becomes easy to solve if one knows some extra piece of information. Of course, private key crypto systems have not disappeared. Indeed, they are more important than ever, since they tend to be significantly more efficient than public key crypto systems. Thus, in practice, if Bob wants to send Alice a long message, he first uses a public... So there you go. In practice, if Bob wants to send Alice a long message, he first uses a public key crypto system. See, I don't really get why it words it like that, saying, there's no public key crypto systems, and then it says you use a public key crypto system. I think they just word it weird. I don't know what they're trying to say, but I'm just going to move on. And then you kind of use that to get your session started, and then once the session has started, you kind of use the private key system afterwards to encrypt and decrypt the messages. The most efficient modern private key crypto systems, such as DES and AES, of course, no longer used, rely for their security on repeated application of various mixing operations that are hard to unmix without the private key. Thus, although the subject of private key cryptography is of both theoretical and practical importance, the connection with fundamental underlying mathematical ideas is much less pronounced than it is with public key cryptosystems. For that reason, this book concentrates almost exclusively on public key cryptography. So basically, this book is saying that even though private key crypto is widely used, the math in public key crypto is more interesting, and therefore the book is focusing on that. Good thing too, because now, almost 20 years later, pretty much only public key crypto is used for the most part. In my understanding, again, I could be wrong. I'm sure private key crypto is used in many aspects for many reasons. But in the blockchain space, at least what I'm most used to, it's a lot of public key crypto. Modern mathematics, I guess not for hashing and stuff. I guess that's still private. Anyways. Modern mathematical cryptography draws on many areas of mathematics, including especially number theory, abstract algebra, groups, rings, fields, probability, statistics, information theory. So the prerequisites for studying the subject can be formidable. Agreed there. By way of contrast, the prerequisites of reading this book are minimal, praise the Lord, because we take the time to introduce each required mathematical topic in sufficient depth as it is needed. Thus, this book provides a self-contained treatment of mathematical cryptography for the reader with limited mathematical background, which is me. For those readers who have taken a course in, let's say, number theory or abstract algebra or probability, we suggest briefly reviewing the relevant sections as they are reached and then moving on directly to the cryptographic applications. This book is not meant to be a comprehensive source for all things cryptographic. In the first place, as is already noted, we concentrate on public key cryptography, but even within this domain, we have chosen to pursue a small selection of topics to a reasonable mathematical depth, rather than providing a more superficial description of a wider range of subjects. We feel that any reader who has mastered the material in this book will not only be well mastered for further studying cryptography, but will have acquired a real understanding of the underlying mathematical principles on which modern cryptography is based. However, this does not mean that the omitted topics are unimportant. It simply means that there is a limit to the amount of material that can be included in a book, of course, of reasonable length. As in any text, the choice of particular topics reflects the author's taste and interest for the convenience of the reader. The final chapter contains a brief survey of areas for further study. So, I plan to go through this entire book. Mainly because this book does not go through everything anyways, but does give a brief survey of a lot of topics and goes deep into the mathematical backgrounds of a lot of topics. And I think as long as I have that mathematical background, as you can see, the math in cryptography is used. There's so much different types of math, and so going to a different textbook after this should be quite easy. If it has math in it, because this should have talked about it hopefully in the past. So, introduction again, a guide to mathematical topics. This is all this introduction stuff still, don't worry. This is all before the 1 point anything. So, this book includes a significant mathematical material. The following is designed to help coordinate the topics as we cover in a class. So these are all just the mathematical topics. Intended audience and prerequisites. Okay, I'm not going to go through this, and I'm not going to go through syllabus. Further notes. I think we're okay. And there you go. Let's get to it. Nothing that important in the introduction, which is for me to remember and never go back to. So, simple substitution cipher. Oh my gosh. I need to get that Zephyr. There's some kind of PDF textbook thing that I keep forgetting about, that that you can kind of put your PDF into, and it helps you kind of highlight and take notes and all of that. And I think it works with Obsidian too, and you can take notes together. I keep forgetting about it, and hopefully this week maybe I'll finally get to it. So here you go. Oh, here we go. As Julius Caesar surveys the unfolding battle from his hilltop outpost, an exhausted and disheveled courier bursts into his presence and hands him a sheet of parchment containing gibberish. A bunch of gibberish. Within moments, Julius sends an order for a reserve unit of charioteers to speed around the left flank and exploit a momentary gap in the opponent's formation. How did this string of seemingly random letters convey such important information? The trick is easy. Once it is explained, simply take each letter in the message and shift it 5 letters up the alphabet. Thus, J in the ciphertext becomes E in the plaintext, because E is followed in the alphabet by F, G, H, I, J. Applying this procedure to the entire ciphertext yields enemy falling back, breakthrough imminent Lucius. The second line is the deciphered plaintext, and breaking into the words and supplying the appropriate punctuation reads the message, this thing I just said. There remains one minor quirk that must be addressed. What happens when Julius finds a letter such as D, right? There is no letter appearing 5 letters before D. The alphabet starts at A, it goes A, B, C, D. D is the 4th letter. And so if you go 5 letters before A, you get like A minus 1 or something. And so like, what is that? That is just Z. Or wait, is it Y? Oh, it's Y. The answer is that you must wrap around the end of the alphabet. So I guess Z is 4. Anyways. Since Y is followed by, Z, A, B, C, D. This wraparound effect may be conveniently visualized by placing the alphabet A, B, C, D, whatever, around in a circle, like a clock, rather than a line. If a second alphabet circle is then placed within the first circle, and the inner circle is rotated by 5 letters, as illustrated in Figure 1.1, the resulting arrangement can be used to easily encrypt and decrypt Caesar's messages. To decrypt a letter, simply find it on the inner wheel and read the corresponding plaintext letter from the outer wheel. To encrypt, reverse this process. Find the plaintext letter on the outer wheel and read off the ciphertext letter from the inner wheel. And note, if you build a cipher wheel whose inner wheel spins, then you are no longer restricted to always shifting by exactly 5 letters. Cipher wheels of this sort have been used for centuries. Very exciting. So you can kind of edit your cipher wheel so that it's not just 5 letters each time, but you can kind of spin and change it to be any number of letters, which I guess the only ones that matter are 26. Or from 1 to 25, I don't know. Although the details of the preceding scene are entirely fictional, and in any case it is unlikely that a message to a Roman general would have been written in modern English, there is evidence that Caesar employed this early message of cryptography, which is sometimes called the Caesar cipher, in his honor. It is also sometimes referred to as the shift cipher, since each letter in the alphabet is shifted up or down. Cryptography, the method of concealing the contents of messages, comes from, I'm going to take this because it's like an obvious definition, but I'm going to start putting definition beside them so it comes up in my notes. This doesn't look great, but it looks alright. Okay. I feel like maybe I should just start copying and pasting definition, because it's probably just going to be a lot of definitions. I think Caesar cipher, shift cipher is pretty straightforward. Maybe one day I'll forget. So I'll just be like, cipher. Did I spell Caesar wrong? I did spell Caesar wrong. I mean, literally just very straightforward. I don't know how I could ever forget that. But hey, things can get forgotten. Okay. In the Caesar cipher, each letter is replaced by one specific substitute letter. However, if Bob encrypts a message for Alice using the Caesar cipher and allows the encrypted message to fall into Eve's hands, it will take Eve very little time to decrypt it. All she needs to do is try each of the 26 possible shifts. Bob can make his message harder to attack by using a more complicated replacement scheme. For example, he could replace every occurrence of A by Z, and every occurrence of Z by A, and every occurrence of B by Y, and every occurrence of Y by B, and so on, exchanging each pair of letters, Z to X, M to all the way to M to N. This is an example of a simple substitution cipher. That is, a cipher, okay, well, apparently, a simple substitution cipher is a cipher in which each letter is replaced by another letter. The Caesar cipher is an example of simple substitution, but there are many other than the... Fine. I'll just take this note so I can just get it all written down. And in case I somehow forget what a substitution cipher is, which would be quel dommage, right? Okay. There's some like information here, like cipher wheels, alphabets, and yeah. So this is kind of what the cipher wheel looks like. How you can like shift the letters to be different letters, and you know, hopefully it makes sense to most people. A simple substitution cipher may be viewed as a rule or a function where these letters are going to these letters, assigning each plain text letter in the domain to a different ciphertext letter in the range. To make it easier to distinguish the plain text from the ciphertext, you write the plain text using lowercase letters and the ciphertext using uppercase letters. So plain text, ciphertext. Note that in order for decryption to work, the encryption function must have the property that no two plain text letters go to one same ciphertext. The function's properties had to be one-to-one or injective. I'm too tired to write definition every time, so I'm just actually, I'll do it. Oh no, and then this. Maybe the Vim functions would make this faster, honestly, because like, not sure, because you can use Vim settings on Obsidian. A convenient way to describe, actually I should maybe just typo. I'm just gonna propose changes this time. Just to get this added. So I added with, it went down a bit. Create pull request. Sorry. Back to the text. A convenient way to describe the encryption function is to create a table by writing the plain text alphabet on the top row and putting each ciphertext letter below the corresponding plain text letter. Example 1.1, a simple substitution encryption table is given in table 1.1. The ciphertext alphabet, which is the uppercase in the bottom row, right, is a randomly chosen permutation of the 26 letters in the alphabet. in order to encrypt the plaintext message 7 years ago. We run the words together, look up each plaintext letter in the encryption table, and write the corresponding ciphertext letter below. So we have 7 years ago. There's a random permutation, which is then written in 5-letter blocks. So when you encrypt something, you typically write it like this. So if you're like a spy reading some encrypted message, you might read, this type of thing, and then when you decrypt it, you'll, add the punctuation and the spacing, however you need. So this is a simple substitution encryption table telling you how to encrypt the alphabet. So you have the alphabet on top, and it's telling you what letters go to them. And then a simple decryption table where, again, you have the alphabet on the bottom, right? This is the ciphertext, and it's telling you that's how you decrypt back to the plain text. So there you go. And this would be the message that you would get. And if you got that message and you know that it was encrypted using table 1.1, we can reverse the encryption process by finding each ciphertext letter in the second row of table 1.1. So if you have G here, the capital G, which makes it a bit easier to know where you're going, but you need to find it in there you go, and you just go through the entire thing. And decrypting is easier because, again, it's in order here. So G and here, G and here. For decrypting, it's in order at the bottom. However, since letters in the second row are all mixed up, it's somewhat inefficient. It's probably better to make a decryption table, which is table 1.2. And there you go. Need new salad dressing, Caesar. So there you go. This should be relatively self-explanatory. You kind of just probably do this in like grade school, like in math class. So cryptanalysis of simple substitution ciphers. So here's the actual fun part, in my opinion. So we know about the cipher. Now we're going to talk about actually breaking the cipher, which typically is where I enjoy spending my time. I'm definitely not. Anyways, how many different simple substitution ciphers exist? We can count them by enumerating the possible ciphertext values for each plaintext letter. First, we assign the plaintext letter to one of the 26 possible ciphertext letters, A to Z. So there are 26 possibilities for the plaintext A. Next, we are not allowed to assign B to the same letter as A. We may assign B to any of the other remaining 25 ciphertext letters. So there are 26 times 25 equals 650 possible ways to assign A and B. We have now used up 2 of the ciphertext letters, so we may assign C to any of the remaining 24 ciphertext letters, and so on. Thus, the total number of ways to assign the 26 plaintext letters to the 26 ciphertext letters using each ciphertext letter only once is 26 times 25 times 24, all the way down to you get to Z, which is the 1, so 26 factorial, which is this huge number over here, which seems huge, right? It's not that big though. It's only 10 to the 26. So there are 10 to the 26 different simple substitution ciphers. Each associated encryption table is known as a key. So this entire table, right, is known as your key. Your encryption key, your decryption key. Suppose that Eve intercepts one of Bob's messages and that she attempts to decrypt it by trying every possible substitution cipher. The process of decrypting a message without knowing the underlying key is called cryptanalysis. And I'm not going to write definition this time, even though I kind of want to, but that just takes very long. Not that long, but longer than just moving on to the next one. That was weird. If Eve, or her computer, more realistically these days, is able to check 1 million cipher alphabets per second, it would still take her more than 10 to the 13 years to try them all. But the age of the universe is estimated to be on the order of 10 to the 10 years. Thus, Eve has almost no chance of decrypting Bob's message, which means that Bob's message is secure and he has nothing to worry about. Or does he? I like this textbook. It is time for an important lesson on the practical side of the science of cryptography. So this is, I guess, important. I'll take the note because it is a mindset that I don't think everyone always takes into consideration in the area of cryptography, where your adversary is always, coming at you with their strongest weapon, and even if your whole house is super strong, but you have one weak link, like one window is a bit, raggedy, then they're gonna attack the window. Like, you could be spending all your resources making your doors safe, making your roof safe, making your walls safe, and then they come attack your window, and you're like, oh man, well now they're in my house. So as a defender, it's a lot more difficult. Whereas as an attacker, cryptanalysis, you really only have to find one weak link in the entire system. So let's put these notes up a bit. Decrypting, I should probably add that to the dictionary. Injective, I'll add that to the dictionary. And plain text, definitely adding that to the dictionary. Okay, I don't know why it's not auto giving me bullet points. That's okay. Despite this large number of possible simple substitution ciphers, they're actually quite easy to break. That's pretty interesting, right? And indeed, many newspapers and magazines feature them as competition to the daily crossword puzzle. The reason that Eve can easily cryptanalyze a simple substitution cipher is that the letters in the English language or any other human language are not random. We speak with rhythm, not randomness. To take an extreme example, the letter Q in the English language is virtually always followed by the letter U. As I said, there's some sort of rhythm there. More useful is the fact that certain or pattern, maybe more than rhythm. I like the word rhythm for that, though. Certain letters such as E and T appear far more frequently than other letters such as F and C. Table 1.3 lists the letters with their typical frequencies in the English text. As you can see, the most frequent letter is E, followed by T, A, O, and N. Thus, if Eve counts letters in Bob's encrypted message and makes a frequency table, it is likely that the most frequent letter will represent E. So this works. The longer the message is, the easier it is to be able to cryptanalyze in this way. Obviously, if the message is short and there's lots of T's or lots of N's, you might get confused. But because of that pattern and that rhythm that doesn't change in the English language or in any language, the longer the text is, the easier it'll be to know that the most frequent letter actually is E. And there's other kind of patterns you can use. This text goes through quite a few of them. In this way, Eve can try various possibilities, and after a certain amount of trial and error, decrypt Bob's message. In the remainder of this section, we illustrate how to cryptanalyze a simple substitution cipher by decrypting the message given in Table 1.4. Of course, the end result of defeating a simple substitution cipher is not our main goal here. Our key point is to introduce the idea of statistical analysis, which will prove to have many applications throughout cryptography. Although for completeness, we provide full details, the reader may wish to skim this material. So I will skim this material. I think it's pretty obvious that E is the most frequent letter in the alphabet appearing, decreasing frequency in alphabetical order, and you can kind of see how you can use that to be able to, some letters appear together, and so you can actually dig in and kind of continue to, read this message and dig in. And yeah, it's actually a pretty interesting read. I would suggest taking the time to read it if you ever find yourself going through this and would like to take some time. But I'll be skipping it for now. Oh yeah, this was the paper. Okay, so now we're getting to more fun stuff. Again, that was pretty slow. Divisibility and greatest common divisors. I think we're getting to a point of the text that I said I have to pay attention to. So let's see. I said pay attention to 1.2 to 1.5. It's saying 1.11a, but that's making me feel like maybe that's something different. Because 1.11a, I don't think modular fast. Oh yeah, it's saying page 19. Oh, and there's a bunch of exercises. Okay, I should do more of the exercises, but let's go to page 19 first. Page 19? I passed that a long time ago. I missed something. Oh no, I didn't get to page 19 yet. I'm good. So why is he... Oh, proposition 1.11a. Confusing me. Theorem 1.1, extended Euclidean algorithm, A. Okay, I understand now. Sorry, I just wanted to make sure I was... Yeah, chapter... This gets way more into the math very quickly. Okay. Much of modern cryptography is built on the foundations of algebra and number theory. So before we explore the subject of cryptography, we need to develop some important tools. In the next 4 sections, we begin this development by describing and proving fundamental results from algebra and number theory. If you've already studied number theory in another course, a brief review of this material will suffice. But if this material is new to you, then it is vital to study it closely and to work out the exercises provided at the end of the chapter. So that, to me, is this. It's not necessarily new to me, but still, I think that doing the exercise at the end of going through this chapter fully, going through all the exercises in the chapter, will really help me have like I used to never do homework as a kid, just do the exams and try my best. So I think breaking that habit now and just doing the homework at the end of the textbooks will be a great fit for me. And so number theory is the study of natural numbers, or more generally the study of integers, so you could have negatives or positives. I don't think I need to write that down. The set of integers is denoted by the symbol Z. I'm not sure if that's math cal, so let's just do number theory is the study of ints. So you have like a set of -2, -1, 0, 1, 2, and then denoted by the symbol. I don't know if it's math cal. Z. Whoops. Z. Nope. Am I even gonna remember what this is called? Oh, my back. Draw latex. There you go. I don't know why I drew it like that. I always draw it like that. Why am I so bad at this today? Duh, 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 duh. Okay, I know my Z isn't that bad. Come on, guys. What? What? That was weird. Okay, come on. I can do this. 1, 2, 3, 4. I did all right. I did okay that time. Show more. It's just a Z, guys. It's just a Z. And I can just look up. Okay. Is it written the right way? I'm pretty sure I'm doing it the right way. Yeah. Okay, maybe it's like Z. How do you do this? Okay, let's try this one more time. It goes like that, and then like that, and then like that, and then like that. I'm having fun. Okay, now I do it. Oh! Oh my god, I went away. There you go. Math DS. Okay. All of that math DS. Is that going to work? No! See, I knew that wasn't going to work. Math mode. Use package. DS font. I don't have package. DS font. Interesting. Math cal. Ugh, fine. I'll just latex symbol for real number. Oh gosh. Sorry, integer. Whatever. Math BB. Oh my gosh. It's definitely Math BB. I've done this way too many times yeah. Anyways, integers can be added, subtracted, and multiplied in the usual way, and they satisfy all the usual rules of arithmetic, commutative law, associative law, distributive law, etc. The set of integers with their, so yeah, integers, sorry, not real numbers, integers, wow, oh gosh. Yeah, I just wrote that ints. Anyways, just let me be. The set of integers with their addition and multiplication rules are an example of a ring. The set of integers, let's just take that down. Why? What the flipperjacks? You just try to be the set of integers. Interesting stuff, my guy. So, section 2.10.1 for more about the theory of rings. Sounds very interesting, actually. If a and b are integers, then we can add them, a plus b, subtract them, a minus b, and multiply them, a times b. In each case, we get an integer as the result. This property of staying inside of our original set after applying operations to a pair of elements is a characteristic of a ring. I don't know why it's being so frustrating when I copy and paste different things on different lines. Because now I want here, and that to go there. I mean, like, I don't know. There you go. Simple enough. But if we want to stay within the integers, then we are not always able to divide one integer by another. For example, we cannot divide 3 by 2 since there's no integer that's equal to 3 over 2. This leads to the fundamental concept of divisibility. This actually, in my opinion, this whole page, like this whole intro of the chapter is such a wonderful intro to the subject, in my opinion. But anyways, we have a definition here. Let a and b be integers with b not equaling 0. We say that b divides a, or that a is divisible by b if there is an integer c such that a equals b times c. We write b with a little line there to a to indicate that b divides a. If b does not divide a, we write b liney thingy with a cross through it, a. So b divides a, b does not divide a. And b divides a only if a equals bc. And I mean, it's a definition, I guess, of being divisible, but probably one of the few different definitions I don't actually need. I actually understand that one. So here's an example which starts to get much more complex very quickly. We have 847, divides into 48,5,331. Since 48,5,331 equals 847 by 573. On the other hand, okay, I'm not going to read all these out. This does not divide this, since when you try to divide it, you get a remainder, right, of 83. More precisely, this is what you get, plus some remainder. So it's not an exact multiple. Here's a remark. Notice that every integer is divisible by 1. The integers that are divisible by 2 are even integers, and the divisible that are not divisible by 2 are odd integers. There are a number of elementary divisibility properties, some of which we list in the following proposition. So, let a, b, and c be an element of, or I guess be integers. If a divides b and b divides c, then a also divides c. If a divides b and b divides a, then a is equal to some multiple of b, I guess. Like b plus or minus, so same thing. A is a multiple of b. If a divides b and a divides c, then a divides b plus c and a divides b minus c, so c is also a multiple of, I guess, a and b, I guess, or b specifically here, but probably a too. And you gotta prove them. I'm not a proof person. I should work on that, but not so far. Now we get into the fun definitions. So, a common divisor of two integers, a and b, is a positive integer d that divides both of them. So, a positive. So, let's just take that down. This happens a lot, I guess. Do. I figured it. Okay. The greatest common divisor of a and b is, as its name suggests, the largest positive integer, d, that, okay, well, I feel like I might need some of this now. Okay, well, this is the actual definition. If there is no if there's no possibility of confusion, it is also some sign denoted by A, B. If A, B, and B are both 0, then GCD is not defined. Such that D divides A and D divides B. So D needs to be a divisor of both, yeah. It is a curious fact that a concept as simple as the greatest common divisor has many applications. We'll soon see that there is a fast and efficient method to compute the greatest common divisor of any two integers, a fact that has powerful and far-reaching consequences. Example 1.5. The greatest common divisor of 12 and 18 is 6, since 6 is divides into 12, and 6 divides into 18. And there's no larger number with this property. Similarly, the GCD of, and I wonder if this was what I had here. Let's see. If I do 784 and 2024, yeah. So this is what I had here. I have, for some reason, I just cannot put it on the screen. But let's kind of go here again. So it's relatively straightforward to do GCD, at least. So I guess I could, well, let me, oops. Cargo run first, then 748, 2024, and then it's 44, and then let's see, cat, I guess, cat, okay. So, I don't know why my screen's being super weird, but you have the library, nice little main thingamabob, very fun. But basically, like we said in the text, we have A and B, and well, this is just taking in the A and the B and putting it through. So this is the actual fun stuff. So yeah, you're pretty much going through and producing the factor, returning the factor A, and basically continuing to find the mod of B until A is equal to, like you have the greatest equal. And I guess if you get 1, then what's it called? Then I guess like there's no, they're not, like they're prime. Then you know like they're both numbers are prime with each other. So that's not a very good example or explanation of the code, but I have all like the comments and everything in. Oh wait, did I? Oh, did I not add comments to this one? I think I removed the comments. My bad. But same type of thing. It goes through all the divisors, so it finds all the divisors, and then it goes through and just finds until they're it goes up, finds until they're the same, and then once they're not the same, it returns the one that's the highest. So yeah, that's what's happening right there. The key to an efficient algorithm for computing greatest common divisors is division with remainder, which is simply the method of long division that you learn in elementary school. Thus, if a and b are positive integers, if you attempt to divide a by b, you get a quotient q and a remainder r. So how many times did you kind of have to multiply or divide, and then what's left over? And then yes, r is obviously smaller than b. So in this example, 230 is divided by 17 and gives a quotient of 13 with a remainder of 9. What does this last statement really mean? It means that 230 can be rewritten as 17 times the quotient plus the remainder, where the remainder is 9 is strictly smaller than divisor 9, 17. The definition, the division algorithm, let a and b be positive integers, let a divided by b has a quotient q and a remainder r, means that, okay, this is just very straightforward though. The values of q and r are uniquely determined by a and b. Suppose now we want to find the greatest common divisor of a and b. We first divide a by b to get a equals b times the quotient plus the remainder. If d is any, if the divisor is any common divisor of a and b, then it is clear from the equation that d is also a divisor of r. If d is any common divisor of a and b, I'm not even seeing d in the equation, so that's just annoying. But if you're trying to find a common divisor of a and b, I guess they're saying that that obviously it has to be a divisor of r, because it needs to be able to a divisor of both sides of the equation, I guess. See proposition 14, 1.4c. And so it's talking about this one here. If a is a divisor of b and a is a divisor of c, then a is a divisor of a of b plus c, and a is a divisor of b minus c. So this is b plus c. Okay. Similarly, if e is a common divisor of b and r, then 1.1 shows that e, I don't know, now you're bringing e into things. E is a divisor of a, because e is a divisor of b and r, and d it is a divisor of r. So if something's a divisor of r, then it's, sorry, if d is a divisor of a and b, it's a divisor of r. If e is a divisor of this side, b and r, then it's a divisor a and b, r, b and r, a. Okay, that makes sense. In other words, the common divisors of a and b are the same as the common divisors of b and r. The GCD of a and b is the same GCD as b and r. I feel like I understand this, but I'm missing like something still. It makes sense. It's just, we're gonna move on, but that's fine. We repeat the process dividing B by R to get another, pages 12, to get another quotient and remainder. So B equals R times some other quotient and remainder with, R prime being between 0 and the original remainder. See, this, I need to write this out or something, on my tablet or something. Then the same reasoning shows that, okay, so the GCD of A and B, which is the D, because D is equal to E, I guess, equals the GCD of B and R, so which is E. And now here, the GCD of B and R, okay, and then R and R, and you just skip this, you just totally remove this, the Q and the Q prime. Okay, 1 second. I think I have to go, but I'll be back, maybe.